So I don't know about you, but to me the fact that our sun is just a member of one galaxy, and they're like hundreds of millions of galaxies in the universe. Um, it's it's humbling. We're switching gears, kind of going out a little bit more, and of course we need to talk about that ever important little unit of stars we call a galaxy. And so our sun, excuse me, well, our galaxy is called the Milky Way galaxy. And we think you're going to see some photos of other galaxies here in a minute. Although we've never had a photo kind of looking at the face of our galaxy, we think that the Milky Way has spiral arms. More later in the Milky Way in general. But if we were to kind of hone in on our cosmic address, okay, of course we are that pretty blue marble, okay, big pale blue dot. And so we are just one planet that's orbiting the sun. There's kind of a soul representing our solar system. And here this is representing our Milky Way galaxy. And we'll talk more about it, but we are about, if you draw, from edge to edge, it's kind of like the Monty Python song says, we actually are about halfway from the bulge, what we call the bulge, the center, to the edge of the Milky Way galaxy. And does it look like a frisbee? Does it look like a flat disk? Because it is. Let's see. Then the thing is galaxies like ours, and ours are organized in what we call clusters. Okay, so there's a cluster of galaxies called the local group. Okay, so we are a member of the local group. And then clusters of galaxies are organized by forming what we call superclusters, and we are a member of the local supercluster. You would think we could be a little more original than that. I don't know. Okay, so and then the way the universe in general then is depicted, you'll kind of see. Can you? I don't know. I'll just kind of zoom in on this. Then oftentimes you'll see something kind of like this: the fabric or the web, not the fabric, but what's out there in the universe. And when you see this sort of thing, each one of those dots represents a galaxy and or a cluster or supercluster of galaxies. The universe is kind of uneven. Well, it is, but it isn't in terms of the distribution of galaxies. Starting with the Milky Way galaxy. So one of the things this semester I'm hoping that you're able to kind of spend some time looking at, if you haven't already, is what we call the Milky Way. And the Milky Way is actually a band of stars that goes from one horizon over to the other horizon. And that band of, I say band of stars, and maybe even kind of like dark, what we call dark lanes. I don't know if you can kind of see some dark lanes there. But that is looking into the plane of our Milky Way galaxy. So this would be above the plane, and this is below the plane, or vice versa. And somewhere in the middle there is the center of our galaxy. Okay, so that's what we call the Milky Way. And this, I mentioned that though we have not been above the plane of our galaxy to see it, this is what kind of the face-on, what we say the face-on perspective of what our galaxy might look like. Kind of see the spiral arms. Okay, so what else is out there? Okay, we got stars with planets in orbit about them. We got galaxies. Well, actually, within our own galaxy, another very cool celestial object that we enjoy looking at. I'll kind of go ahead and just zoom on this. Doesn't that look like maybe clouds and looks like fog? Okay, fog actually is particles of liquid water that's kind of making the light kind of do things that so we can see that liquid water's there. But this actually, these are particulates. These are particles. I've recently heard them described as when astronomers talk about dust, okay, so dust out there, they're actually talking about things that are pebble or rock size. I don't know. So in general, in outer space, or the space between stars, interstellar space, when you run into a region of space like this that has material other than being a vacuum, that's what we call a nebula. and there's different types of nebula, and actually could see them in the same region. For instance, we'll talk more about nebula, but for instance, do you see emission nebula? Okay, we see dark nebula here, reflection nebula here. Okay, this is all part of, you need binoculars or a telescope. You need a telescope to see it that cool. Okay, but even with binoculars, if you look close at the constellation Orion, okay, even with binoculars, if you look in the, let me kind of orientate you with regard to Orion. Most people really like seeing those three belt stars of Orion. If you see those, and they're striking because they're kind of have the same distance between the stars. But if you see that, then you might kind of pick out the kind of the, I think of it as like a toga, kind of the shoulders of Orion, the hunter, okay, kind of up there, and this is kind of his knees, the belt, and then this region right here is what we call the sword region. So he has like a dagger or sword hanging down from his belt, and that region is where you're going to see that nebula. Okay, it's awesome. Kind of with the whole nebula thing. Here's a picture of a different nebula. Very pretty. You can kind of see some dark lanes, perhaps, and a couple things. So that interstellar gas cloud can actually be great for stars to be born in, and oftentimes, though, that dust is actually given off of stars that have lived their lives and given it back to. So here's some more nebula. Looks kind of gassy, doesn't it? What these all have in common, these are a type of, I guess would you call them emission nebula. They're a type of emission nebula that actually, planetary nebula came from, I'm going to try to write here, dying stars. Oh, I can't spell either. Sorry. Okay, we're going to see that stars don't live forever, and kind of dependent upon how massive they are, they'll have different life cycles, or, you know. So the thing is, in every planetary nebula, you'll see a central star that is kind of dying, okay? So planetary nebula don't have anything to do with planets, and I think historically they got the name planetary nebula because they kind of have a spherical, some of them, not all of them, have a spherical look to them. Okay, so anytime somebody says, oh, that's a planetary nebula, think dying star. And what's happening is that star is dying, and it's kind of, gravity is kind of losing out, weakening, and it's kind of losing its outer material. So one other thing, we do this a lot in astronomy. So these are all three examples of planetary nebula, but they have proper names. This took me a little while to sink into my head. So for instance, this is called the Helix Nebula. It's a planetary nebula. Okay, this is a planetary nebula too. Can you see kind of the central star? And its proper name is the Carpenter's Level. Okay, and a third planetary nebula up here kind of takes on an hourglass shape. And so, like, for that reason, it is called the Hourglass Nebula. But they are all three planetary nebula. Those are within our solar system. So, I'm sorry. They're not within our solar system. Go back to the nebula. Okay. These are all, just so we're on the same page here, okay, these I mentioned came from dying stars. So these nebula are great shots of dying stars that were part of the Milky Way galaxy. That's what I want to say. They're all part of our galaxy. That's important to put things in perspective. This is a photograph of another galaxy. Okay, this is a classic. I saw this the other night at the observatory. Gorgeous. This is the Andromeda Galaxy. So it wasn't until the 1920s that scientists actually understood the concept of a galaxy of stars. But the Andromeda Galaxy, this is actually three galaxies. Okay, you see this big one here, that's Andromeda, and there's a little one here, and there's a little one here. They're companion galaxies to Andromeda. Isn't that cool? Gorgeous. Let's see, what else was I going to say? So, those galaxies are another celestial object that we can enjoy looking at from Earth, and plus we need to ponder what's up with galaxies? How did they get there? And how do we fit into that? Oh, one more thing. If you've ever heard that this galaxy, Andromeda, is actually on a collision course with the Milky Way galaxy, that is correct. Back and forth a little bit in my notes here, but just bear with me. These are two types of groups of stars. We call a group of star a star cluster. Now these star clusters actually are associated with our galaxy, the Milky Way again. And there's two types of clusters of stars. There are open clusters of stars, and then the next photo I'm going to show you right next to it is a cluster of stars called a globular cluster of stars. But if you've ever heard of the Seven Sisters, it's an awesome through binoculars. It is so cool through binoculars. The Seven Sisters are part of. Have you ever heard of the constellation Taurus? I bet you did. Taurus the bull. Actually, this group of stars called the Seven Sisters is also called M57. We'll be talking about M numbers this semester. But this group of stars, sometimes it's called, and I'm kind of embarrassed to say this, but I know why students say it. It's called the Little Dipper, and you'll see what I mean. Okay, it is. I hesitate to call it the Little Dipper, but I will say that I'll try to show you when we're out viewing that it's not close at all to the Little Dipper. The real Little Dipper is a subset of stars of Ursa Minor. It's not close in size to that at all, but it kind of takes upon that shape. All right, so open clusters. The thing about open clusters and globular clusters is this is a group of stars that were born about the same time. They're like cousins, and they were born in what we call the same nursery, stellar nursery. Isn't that neat? So let's see. The other type of cluster of stars, isn't this gorgeous? Okay, this globular clusters is one of my favorite. They look three-dimensional through a telescope. And this is actually the globular in Hercules, the constellation Hercules, so we call it the Hercules cluster. Actually, there's two. There's this one and M92, but it's just awesome. These tend to be old stars, and we'll talk more about that later. Okay, but these clusters of stars are associated with the Milky Way galaxy. Okay, so and this particular object is called M13. What else can we see up there? Well, we can see black holes. And this is where especially kids will say, no, you can't see black holes, and they're right. You can't see black holes, but we can know that they're there. And we especially know that they're there when material is queuing up to go in them. It forms what we call an accretion disk. And as it falls in, it creates or cycles towards the location of the black hole to fall what we call beyond the event horizon, no longer to be seen again. It gets very hot and emits radiation. So this little hint over here, our snacking black hole, I think I linked to that in my playlist of videos for our later chapter on black holes. Let's see, what else do we have? Here's my cue to, well, maybe not. Okay, so black holes, I guess one thing I would link with black holes is we are finding that most galaxies, these are 3 galaxies. Aren't they awesome? Well, 3 galaxies, but here, this is Andromeda again, and can you see the 2 companion galaxies to Andromeda? Okay, and these are other galaxies. Most galaxies have what we call a supermassive black hole in their center. Let's see. Kind of. Okay. So, I don't know if this will work for you, but with my background in chemistry, one of the things we need to talk about in general chemistry is the concept of a system and the system's barrier. Let's see. I'll draw a little picture here. I don't know. Just bear with me. So this is my beaker, okay? And a lot of times in chemistry, we'll put stuff in the beaker. This is my stuff of interest. Okay, so that's my system. Okay, and then I have a barrier. I'll put B for barrier. And then I have the surroundings. Okay, that's outside the system. And this whole thing is what we call the universe. I don't know. Anyway, in astronomy, it is sort of like that. But in astronomy, it's when we start to kind of count beans, do a balance of what is in the universe. The two things, I guess it's nothing, nothing like I described, but the two things we look at, we need to account for in our universe are matter and energy in our universe. And so everything in our universe is either matter or energy. There's nothing in our universe that's not matter or energy. Another cool thing, and I just now thought of this, was when we talk about the origins of our universe, very, very quickly, a ton of energy was converted to matter. Okay, so it can go back and forth, but it's got to be one or the other, and it will be conserved. All right, so this is a new slide. If you print it up, I'm going to kind of put this down here, because I only want you to pay attention to part of this. Okay, so I don't have built, so I'm building up to something, so just bear with me. You don't have this slide if you printed them off. I don't think you do. So what if you were driving a car and your car was driving at a speed of 60 miles per hour and you talk to somebody on the phone? You're a passenger, not the driver. So I say you're riding in a car. Okay, you shouldn't talk on the phone when you're driving. And so you talk to somebody on the phone and you say, well, we're 30 minutes away. And, you know, it's kind of understood that road, you know, you can drive 60 miles per hour. Well, if you're 30 minutes away and you're driving 60 miles per hour, can you see where you must be 30 miles away? Does that make sense? Because you're driving 1 mile per minute. All right. So let's take that up a notch. Let's say, and I don't know how this would work, but let's say instead of going 60 miles per hour, you're going 600 miles per hour. But you say, when you talk to somebody on the phone, we're going 600 miles per hour, no problem, and we're 30 minutes away. Can you see where that means that you can translate that time, knowing how fast you're going, to knowing then that you are 300 miles away? Does that make sense? Well, you know where I'm going with this. Well, let's add a few zeros, and let's say you were going 6 million, you're going 6 million miles per hour. 6 million miles in 1 hour. And you are 1/2 an hour away. You are 30 minutes away. Okay, so can you see where you must be 3 million miles away? Okay, knowing that time. Okay, so just for kicks, if we convert, because you're going to see why in a minute, but if we convert units of miles per hour, so the 6 million miles per hour, if we convert them to kilometers per second, I can't remember what that number is. I need to Google it. So here's the deal, and I'm going to kind of hide this, so we're only traveling. So we're only looking at one of these lines at a time. I'm going to go ahead and going from that fast car that travels very fast. I'm going to go now on to this concept that light travels very fast. I hope you can see that. Light travels very fast. It's kind of neat how they first kind of figured that out. Okay. Specifically, in a vacuum, light travels at 300,000 kilometers per second. Not only light, but all forms of cousins of light, that forms of energy we call electromagnetic radiation. It travels at that speed. Okay? So if we know how fast it travels, then we can talk in terms of time. And that time can be translated to a distance. Here we go. So when light leaves the moon, let's just say sunlight hits the moon, and then that light comes to the earth, okay? It takes that light travel time 1 second. And because it takes that travel time 1 second, and we know it's traveling at 300,000 kilometers per second, if we do the math, we can come up with a distance. We can take that time and turn it into a distance. Let me see. And I did the math, factor label. And so, based upon the fact that light takes 1 second to get here from the moon, we know then the moon must be 300,000 kilometers away. Actually, I didn't have to do any math. That's pretty easy. Because it travels 300,000 kilometers per 1 second. Does that make sense? So, in terms of using time as a distance, we would say that the moon is 1 light second away from us. So we've taken the concept of time, one light second, and we turned it into distance. Okay, isn't that cool? All right, let's look at an object that's a little farther away from the Earth. Okay, again, relative to the Earth. So when the sun sends us light, it takes that light, and light we're going to see light is both a wave and it's a particulate, a packet of energy we call a photon. So when those photons, those little particles of energy reach us, there's a delay. It takes about 8 minutes to get here from the sun. So that 8 minutes, those 8 light minutes, are actually could be we could do the math and we come up with a distance. Okay, and that distance is 1.4 times 10 to the 8th kilometers. Now this is where I'm kind of, I remember why I did this. I'm kind of hoping or assuming that we're kind of okay with the idea of packing up big numbers in scientific notation. I take all the math out of my class, which I probably could get some flack from some people, but that's okay. I take all the math out, but what I need you to be able to understand is when we pack up a number in what we call scientific notation, that what we call exponent, or that superscript of 10, means that we have basically tacked on that many digits after the decimal. So, okay, so kind of looking then at, because we need to, because we can't write all those decimals. So for instance, when I said how many kilometers the sun is from the Earth, and I want 1.4 times 10 to the 8th, basically you have to add 7 zeros after the 4, and that's how many kilometers the sun is from the Earth. All right, let's go a little bit further. Let's go to not the nearest star, but a bright star. And it actually takes 8 years when that star sends its light to us. When that star, and the reason stars, the stars have their own energy is they actually have like little nuclear power plants in their cores. So stars are shining because of nuclear energy in their cores. So when that star Sirius shines energy in all directions, in our direction, it takes 8 years to get to us. So we would say Sirius is actually then 8 light years away. And you can see here then what that translates in terms of kilometers. You have to have put the number 76 and then 12 zeros after that. And that's how many kilometers away that star is. A relatively nearby star. All right. So here we go to our closest, I want to say closest galaxy, the Andromeda Galaxy. So this one just kind of blows my mind. Okay. So light, when we look at the Andromeda Galaxy, by the way, you can see this with binoculars. You can see this galaxy with binoculars. It's kind of, if you've seen that W up in the sky, that's called Cassiopeia. Kind of near Cassiopeia is the Andromeda Galaxy in the nighttime sky anyway. So anyway, it It took light 2.5 million years to get to the Earth. 2.5 million years. So Andromeda is 2.5 million years old. Oh, sorry, darn it. Andromeda is 2.5 million light years away. That's just amazing. In terms of kilometers, that's 24 with 18 zeros after it. Totally, totally amazing. Okay. So are you kind of getting this idea then that if an object is farther from us, it takes longer for the light to get to us. So when the light finally gets to us, basically we are seeing that object as it was long, long ago. Okay, so when we finally get those photons from Sirius, Sirius has aged 2.5 million years. It's just amazing. So this next slide is related to that. Okay, before I kind of get into the whole we're looking back at something old, I just want to go ahead and say what we've been describing on the previous slide is the fact that we can use time, if we know the speed of light, which we do, we can use time light takes to get to us as actually a distance. So when somebody talks about 1 light year, they're talking about 10 trillion kilometers, but they're also talking about the time it takes for, they're talking about an object that it takes 1 year for light to get from the object here. Okay, so the distance of a light year. Okay. So this is kind of a clever figure, I think, from your textbook. And it shows, I love it because I have a little observatory over here with a telescope hiding there. Not hiding, but kind of protected from the elements. And this telescope is looking at some objects. Okay? And you see that this is closest, this is further away, and this is furthest away. So, so this one right here, for instance, this kind of, we're actually going to see a Hubble image of some galaxies coming up, and we're going to see that the farther away they are, the more kind of distorted they look, kind of chaotic. And this is closer. It's a newer. It's not as old. It's a newer galaxy. This is older, and this actually light that finally gets to us from clear out here would be very ancient. Let me draw your attention to what's being shown there. Kind of this brick wall we run up against is called the cosmological horizon. We're going to talk about the Big Bang, affectionately called BB, Big Bang for me anyway. And this is actually the initiation, beginning of our universe. Okay? And the deal is if our universe began 13.7 or so billion years ago, if we try to look 14 billion light years away, it's not happening, because that's beyond our, what we call our cosmos or cosmological horizon. Okay, so I mentioned that the farther away galaxies are, kind of the more distorted those galaxies look. Galaxies early on in our universe looked a little more chaotic than they do now. For instance, these actually were photographs of an assortment of galaxies taken, that these galaxies are in the range of 8 billion light years away. Okay, and these already kind of look a little more distorted than the original photograph we looked at in the first slide in part 1. Now, if you compare that with this, that was 8 billion light years away, these galaxies are 13 billion light years away. So it's not going to be clear to the end of the course that we kind of talk about the evolution of galaxies. But they just don't look as chaotic.